Fellow colleagues, my name is Kevin Raina from the University of Ottawa, and today I'll present my work on empirical Bayesian methods and Bayesian neural networks for medical out-of-distribution detection. Of course, it's important to mention that for more implementation details and a clear idea of the contributions in this work, please check out the paper, and for any questions or clarifications, please contact me at the email address provided here. Deep neural networks have achieved remarkable results in medical imaging tasks, such as radiology, pathology, and dermatology. However, in real-world clinical use, they often encounter out-of-distribution inputs, which contain artifacts like rulers, annotations, or rare disease cases. These can cause confident but incorrect predictions, which is unsafe in medicine. This motivates the need for reliable uncertainty estimation to detect such cases. I'll discuss more about the specific medical imaging datasets soon. Bayesian neural networks help here by modeling weights as distributions instead of fixed values. This allows them to capture both epistemic uncertainty, which is uncertainty from limited data, and aleatoric uncertainty, which is noise in the data or inherent in the observations itself. Now in the upper left corner, we have Bayes' formula that allows us to do posterior inference. But exact Bayesian inference is often intractable, so we need approximations. This is why we try to minimize the divergence between an approximating distribution and the true posterior. This is, of course, variational inference. Now, the variational posterior can, but does not necessarily have to, take the form of a diagonal Gaussian, but it is done for simplicity and faster computation. The prior can also be assumed to be a diagonal Gaussian centered on a zero mean. I would refer to this as a canonical setup of distributional choices, but there is certainly more research to be done here. BNNs also allow us to estimate the predictive distribution by marginalizing over d omega the model weights. The entropy of this distribution is the predictive entropy score. Predictive entropy is one useful measure to flag uncertain cases. It is exclusively used in this work, though I should mention that other scores also do exist. So one practical method is MOPED, which sets priors based on pre-trained deterministic models instead of using vague priors. Essentially, we initialize the prior distribution and surrogate posterior at the weights of a pre-trained deterministic model. Equivalently, we are leveraging earlier information contained in these parameters. Also, the variances of the posterior are controlled to some degree by a delta hyperparameter. This anchors the Bayesian network to a strong baseline while still allowing for uncertainty estimation. As a result, it improves sensitivity to out-of-distribution samples compared to uninformed priors. In this work, I extend MOPED by introducing Gaussian mixture priors. The dual variant equation at the top here uses two different variances around pre-trained weights. This allows for flexible learning, while the hybrid variant combines a pre-trained component with a component that acts as a regularizer, which is significant in small data settings, something we do see often in the medical imaging domain. This provides more flexibility, sharper uncertainty estimates, and better representation of ambiguity. The results are tested on two datasets, D7P, a pathology dataset, and BreastMNIST, an ultrasound dataset. Out-of-distribution cases were images containing artifacts such as rulers and annotations. As shown in this chart, the methods proposed significantly improve over the baseline MOPED, reaching AUC scores of around 80, which is on par with strong existing methods like MBM. This shows that mixture priors lead to more robust OOD detection. To conclude, empirical Bayesian priors enhance Bayesian neural networks for medical OOD detection, offering performance competitive with state-of-the-art approaches. A key point I wanted to make is that BNNs allow us to use a prior distribution, which is significant for OOD detection, since we can leverage earlier information in the model weights and prior distributional form. Though this can be difficult to tune, the combination could certainly prove to be robust in different OOD detection tasks. For future work, I plan to consider priors with more components, test across broader medical datasets, and experiment with new Bayesian scoring functions. Thank you for your attention and listening to this presentation video.